Paris, the summer of 1900. At the Exposition Universelle, Bethlehem Steel set a lathe on the exhibition floor and machined steel at speeds far beyond anything European shops considered survivable. At that heat, a carbon steel tool softens and fails in seconds. This one held its edge, pass after pass, while metallurgists from across Europe crowded the rail to watch. They were looking at the fastest cutting tool on Earth. It kept that title for 25 years. Then a light bulb laboratory in Berlin took it away. If that's your kind of history, like this video and subscribe before the story moves on. The Nile Valley, around 1300 BC. Egyptian craftsmen are turning wood on a bow lathe, and it takes two of them, one hauling a cord back and forth to spin the work, the other holding a bronze edge against it freehand. Rome adds a turning bow. Medieval Europe adds the pole lathe, a springy sapling and a treadle, and for the first time, the turner has both hands on the tool. For 3,000 years, that is the pace of progress. The cutter itself is whatever a smith can forge and harden, and nobody writes down why one edge outlasts another. The machine grows up first. Around 1800, Henry Maunsel builds a screw-cutting lathe in London with the tool locked in a slide rest, driven along precision ways by a lead screw and change gears, repeatable threads, interchangeable parts. The machine can now hold a tool steadier than any human hand ever could, which exposes the real bottleneck. The tooth in the machine's mouth is still plain carbon steel. Hardened carbon steel is a fine material until it warms up. Quench it and it will scratch glass, but let the edge climb past roughly 400 degrees Fahrenheit and the hardness drains right back out of it, in the cut, while you watch the chip color change. That physics caps a turner at around 10 surface feet per minute in steel, maybe 40 in a soft, friendly cut. Every machinist of the era learns to read smoke, because smoke means the edge is already dying. The workaround of the age is feed. A turner can bury a heavy cut at a crawl because pressure is survivable and speed is not, and shop rates across the industrial world are built on that trade. The first crack in that ceiling comes from Britain. In 1868, Robert Forrester Mushet, the metallurgist who had already rescued the Bessemer process, develops a tool steel carrying around 7% tungsten that hardens in still air, no quench at all. Shops call it self-hardening steel, and it cuts harder metal, faster than anything before it. Over the next 30 years, makers swap its manganese for chromium and inch the recipe forward. It looks like a specialty alloy for heavy cuts. It's the ancestor of every tool steel that matters. Bethlehem, Pennsylvania, 1898. Frederick Winslow. Taylor arrives at Bethlehem Steel obsessed with a question the trade thought it had already answered: how fast steel can actually be cut. This is the same Taylor whose stopwatch time studies would make him the father of scientific management. Before he timed men, he timed steel. He teams up with metallurgist Maunsel White, and together they commit heresy. Shop doctrine said overheating ruins tool steel. Taylor and White heat Mushet-type steels toward the melting point on purpose, batch after batch, and log what comes back. Past a threshold every foreman would have called ruinous, the steel returns transformed. It now holds a working edge at a dull red heat, around 1100 degrees Fahrenheit, nearly 3 times the failure point of carbon steel. The trade names the property red hardness, and the material becomes high-speed steel. The experiments behind it were on a scale no machine shop had attempted. By Taylor's own accounting, the program ran 26 years, logged between 30,000 and 50,000 recorded experiments, reduced roughly 800,000 pounds of steel to chips, and cost between $150,000 and $200,000. Out of it came his 1906 paper for the American Society of Mechanical Engineers on the art of cutting metals, and the tool life equation still printed in reference books today. Cutting speed, multiplied against tool life raised to a small exponent, equals a constant for each pairing of tool and workpiece. The exponent is the frightening part. At values common for later carbide on steel, cutting your speed in half can stretch tool life by a factor of 30. Speed is never free. Taylor put a number on exactly what it costs. Handbooks tabulate the exponent to this day, roughly 0.1 for high-speed steel, 0.2 for carbide, higher for ceramics. Paris, 1900, is where the world finds out. Bethlehem exhibits the Taylor White tools at the Exposition Universelle, running cuts at multiples of accepted practice, and Taylor takes the exposition's award for his cutting tools. The Franklin Institute later adds its Elliott Crescent Medal, awarded to Taylor and White together. The numbers land like artillery. Encyclopedia Britannica credits high-speed steel with doubling or tripling the capacity of the world's machine shops, and the shops themselves discover a stranger consequence. Their lathes can't keep up. Existing machines lack the power and the rigidity to feed the new steel what it can eat, and an industry-wide rebuild follows. Heavier beds, bigger motors, stiffer everything. The tool has made the machine obsolete. The recipe keeps sharpening. Crucible steel patents, vanadium editions in 1904, and around 1910 the 1841 composition, 18% tungsten, 4% chromium, 1% vanadium, becomes the benchmark later standardized as T1. Cobalt editions appear by 1912 and push hot hardness further. Molybdenum grades arrive from American mills, Cleveland twist drills Motung among the first, and the Bethlehem 66 composition that became M2, the general-purpose grade still stocked in every tool crib on Earth. Decades later, M42, with 8% cobalt, becomes the grinder room answer for tough alloys. In service, high-speed steel settles in around 70 to 100 surface feet per minute when turning steel, and 70 to 125 when drilling. It still drills, taps, and turns in shops today. But look at the ceiling instead of the floor. Between 1900 and 1927, the benchmark speed for a 60-minute tool life in steel crawls from roughly 80 surface feet per minute to roughly 120. A generation of alloy chemistry buys 50%. The next leap needs a different class of material. There's a bridge material worth naming first. In Kokomo, Indiana, Elwood Haynes patents cast cobalt chromium tungsten alloys in 1907 and 1912 and calls them Stellite, from the Latin word for star, because the polished metal refuses to tarnish. Stellite takes no heat treatment at all. The tools are cast close to shape, ground to the edge, and run as poured, and they keep cutting at temperatures beyond high-speed steel's reach. Lathe tools made from it earn their keep through the First World War. For a moment, cast cobalt looks like the future. The future is being sintered in Berlin instead. Berlin, 1923. The Osram lamp works has a wire problem. Tungsten filament for light bulbs is drawn through dies, and the only dies that survive the job are diamond, bought at diamond prices. Decades earlier, the French chemist Henri Moissan had synthesized tungsten carbide while chasing artificial diamonds, and found a compound nearly as hard, but so brittle it shattered in service. At Osram, Karl Schroeter finds the trick Moissan never had. He mixes fine tungsten carbide powder with cobalt, presses it, and sinters it. The molten cobalt wets and binds the carbide grains into a composite that is both brutally hard and tough enough to use. Schroeter files the patent in 1923, German patent number 420,689. It may be the most consequential piece of paper in machining history. Osram makes light bulbs, not tooling, so the license goes to Krupp. And in April 1926, Krupp begins production in secret before bringing the material to market under a trade name that tells you exactly what they thought of it. Widia, from the German wie Diamant, meaning like diamond. The classic mix is 94% tungsten carbide, 6% cobalt. General Electric moves fast on the other side of the Atlantic. Its metallurgist Samuel Hoyt had visited Osram in 1925, and by 1928, General Electric has a dedicated department selling a competing product under the name Carboloy. Decades on, that business would end up inside Sweden's Seco Tools. What follows is one of the ugliest pricing stories in industrial history, and it sits in the federal court record. In United States versus General Electric, decided in 1948 as part of the post-war reckoning with wartime cartels, the court found that GE, operating under agreements with Krupp, fixed the first American price of cemented carbide at $453 per pound, $1 a gram. At the time, gold sold for about 67 cents a gram. The court also found the cost of production, between 6 and 12 cents a gram. Machinists of the era brazed a sliver of carbide onto a cheap steel shank and touched it up with a diamond wheel, and now you know why. Nobody was going to swing a solid bar of a material priced above gold. Even at that price, shops paid, because carbide moved the ceiling again. It tolerates edge temperatures far beyond high-speed steel, and its working range in steel runs from around 100 surface feet per minute up past 1,000, against high-speed steel's 70 to 100. The 1929 engineering paper introducing Carboloy conceded existing machine tools lacked the rigidity and power to exploit it, and the industry rebuilt its iron a second time in 30 years. Twice now, the machine had to be redesigned around its tooth. Early carbide had a flaw every steel cutting shop found immediately: straight tungsten carbide craters in steel. The hot chip welds to the rake face and gouges a pit behind the edge until the lip collapses. The fix was chemistry, additions of titanium and tantalum carbide alloyed into the substrate, tantalum grades sold under names like Ramet, and one of the men behind it built an empire on the answer. In 1938, metallurgist Philip McKenna developed a tungsten-titanium carbide that ran faster and lasted longer in steel, and founded Kenna Metal in Latrobe, Pennsylvania, to sell it. There's a quiet, full-circle footnote here. In 2012, Kenna Metal acquired the Stellite trademark. Elwood Haynes' Star Metal ended up inside a carbide empire. Then the Second World War made carbide a weapon. Tungsten carbide cores went into armor-piercing shot. Tungsten became a strategic material fought over by every combatant, and the United States pushed molybdenum-based high-speed steels into service partly to free tungsten for the war, while carbide-tipped tooling helped carry wartime mass production on its back. The gray metal in your insert drawer was once contested like oil. The pricing arrangement did not survive the peace. The 1948 ruling went against GE, and in the decades that followed, carbide became cheap enough to grind into solid drills and end mills, whole tools of the material that had once been priced above gold. And the war's aftermath handed machinists a new opponent: jet engines, built from nickel superalloys that work-harden under a dull edge and hold their strength at temperatures that destroy tool materials. That bill comes due later in this story. Before the war ended, the cut itself was finally being understood. Cincinnati, Ohio, 1941. At the Cincinnati Milling Machine Company, Hans Ernst and Eugene Merchant published the first working physics of chip formation, sharpening an approach the Finnish researcher Väinö Pispanen had reached independently in 1937. Their model treats the metal ahead of the edge like a deck of cards, each card shearing forward along a single plane, and Merchant's 1945 equations predict where that plane sits. The practical lesson still holds. Raise the rake angle, cut the friction, and the shear angle steepens, dropping force and power. Machining stopped being folklore and started being engineering. The lab tools were as clever as the theory. Quick-stop devices, some tripped by shear pins and flying hammers, some by explosive charges, yanked the tool out of the cut fast enough to freeze a half-formed chip on the part for the microscope. The frozen chips exposed the machinist's oldest enemy, the built-up edge. Work material cold welding to the tool tip at moderate speeds. Work hardening until it is harder than the parent metal, then tearing away and taking the finish with it. The cure ran the same direction the materials were already pushing. More speed, slicker surfaces. Run fast enough and the metal is too hot to stick. The research also named the 3 ways an edge dies. Flank wear rubs away the clearance face. Crater wear The pit McKenna's chemistry had fought turned out to be diffusion, the hot chip dissolving carbon and tungsten straight out of the tool. Notch where gnaws at the depth of cut line. Nearly every substrate and coating of the next 80 years answers one of those three. The heat numbers frame the whole arms race. In steel, roughly 80% of the cutting heat leaves in the chip, and at carbide speeds, the tool-chip interface can top 1800 degrees Fahrenheit. Carbon steel quit near 400. High-speed steel held to 1100. Every material that follows is a bet on living in that furnace a little longer. By 1957, the material was no longer the bottleneck. The bottleneck was what shops did with it. The brazed tip economy had a rhythm. Braze a carbide sliver to a shank, grind the geometry, cut until it dulls, then grind it again, and again, until there is no tip left to grind. A dull tool came off the machine and went to the regrind bench, where a man restored the geometry by eye and by gauge, differently than the man on the last shift did. The machine sat idle. The geometry drifted. Every edge in the building depended on the best hands in the building. The way out had been waiting for decades. The idea of a replaceable cutting blade traces to Fred Lovejoy's patents back in 1917, and Kennametal had introduced its Kendex indexable systems in 1946. The companies that industrialized it had been preparing longer than anyone realized. Sandvik established its Coromant tooling brand in 1942 and shipped its first carbide tools in 1943. Sumitomo's carbide line, Igetaloy, dated back to 1931, born in the wake of the Widia patents. In 1957, Sandvik demonstrated the T-Max holder in the United States. With mechanically clamped inserts, a machinist could rotate to a fresh corner in seconds. The first product to carry the clamped inserts, oddly enough, was a scraper. Sumitomo launched its throwaway turning line in 1959 and extended it to milling cutters by 1961. The idea sounds almost disrespectful to a craftsman. Don't sharpen the edge. Index it, use it up, and throw it away. It won because the economics were merciless. The cutting edge became a consumable with factory-molded geometry, identical from the first insert in the box to the last. Early flat-top inserts still needed a separate chip breaker plate clamped over the face. Through the 1960s and 70s, the grooves were pressed and sintered directly into the insert, with patents like Kelm's in 1967 marking the shift, and chip control became something you order from a catalog instead of grinding by hand. The groove did double duty. Brittle carbide wants negative rake, a blunt 90-degree edge with mass behind it, and a negative blank flips, 8 corners on a square insert instead of 4, but negative rake buys that strength with force and heat. A positive groove molded into a negative blank returned a free cutting rake while keeping every corner. The ISO designation system turned tool geometry into a shared language. In a callout like CNMG, the first letter is the shape, C, an 80-degree diamond, T, a triangle, S, a square, R, a round, and the characters behind it carry clearance, tolerance, and chip breaker, so an insert ordered in Stuttgart means the same edge in Chicago. The timing mattered more than anyone at those trade shows knew. Numerical control had come out of the MIT Servo Mechanisms Laboratory in 1952, built for Air Force contract work, and as NC machines spread through the 1960s and 70s, the indexable insert was the reason they could run, with nobody standing at the hand wheels. You cannot automate a process that depends on a regrind man's eye. By the 1980s, a machining center could run lights out on a carousel of preset tools, a shift with nobody in the building, unthinkable in the brazed era. One founding story from this era belongs to a shack. In 1952, Steph Wertheimer started grinding cutting tools in a backyard workshop in Nahariya, in northern Israel, under the name Iskar, short for Israel Carbide, and built the company on slide-in blade systems for parting and grooving that made changing an edge as quick as changing a razor cartridge. 50 years later, Warren Buffett's Berkshire Hathaway paid roughly $4 billion for 80% of the group, one of the largest acquisitions in Israeli history. The Shack had chosen the right side of the throwaway revolution. The insert's next transformation was invisible to the naked eye. In 1969, the first coated carbide inserts reached the market, from Widia and from Sandvik, within months of each other, each carrying a film of titanium carbide a few microns thick, laid down by chemical vapor deposition. Sandvik sold its version as the gamma coating and reported performance gains of up to 50%. The physics is simple and brutal. The coating stands between the hot chip and the cobalt binder, cutting friction, blocking heat, and stopping the chip from dissolving the tool underneath it. A film thinner than a human hair became the hardest working layer in the shop. CVD reactors running near 1,000 degrees Celsius learned to stack chemistries: titanium carbide, titanium nitride, titanium carbonitride, capped with aluminum oxide, a ceramic thermal barrier grown right onto the tool, and later, medium-temperature CVD processes deposited tougher, smoother carbonitride layers, with less damage to the edge. Physical vapor deposition followed commercially around 1980 with the gold titanium nitride finish every machinist recognizes on site. PVD runs below 500 degrees Celsius, keeps edges sharp and substrates tough, and leaves compressive stress in the film, so it took over sharp-edged solid tools and interrupted cuts. Then the chemistry raced. Titanium carbonitride for wear. Titanium aluminum nitride, with aluminum that migrates to the hot surface and forms its oxide skin in the cut, the coating that made dry, high-speed machining practical. Aluminum chromium nitride for hot, hard work. Diamond films for aluminum and composites. The coated insert scaled to absurd success. A Sandvik grade, GC4225, became the world's best-selling insert grade in 2005, and today, by Sandvik Coromont's own figures, between 80 and 90% of carbide inserts ship coated. The bare gray insert is nearly extinct. Underneath the coating, the substrate turned into a recipe book. Every carbide grade is a trade between two levers: cobalt content and grain size. More cobalt and coarser grains buy toughness. Less cobalt and finer grains buy hardness, from roughing grades carrying 10% binder or more down to finishing grades near 3. The ISO application system sorted the world's workpieces to match: P for steel-coated blue, M for stainless in yellow, K for cast iron in red, with N, S, and H added later for non-ferrous metals, superalloys, and hardened steel. And for CVD inserts, Kennametal patented cobalt enrichment, a rim a few dozen microns deep where the binder runs up to triple the bulk level, a tough skin under the hard coat that stops coating cracks from running into the edge. Turning geometry took a late leap of its own. In 1997, Sandvik introduced wiper inserts, developed by engineer Ronnie Loff, replacing the single nose radius with a train of blended radii that iron out the feed lines. The rule of thumb stuck fast: double the feed at the same finish, or keep the feed and halve the roughness. Above carbide sits a family of materials for the work carbide can't survive. Aluminum oxide ceramic drew attention from 1938 onward, partly because alumina is dirt cheap next to strategic tungsten, but the early inserts failed the shop test. In the 1950s, the material's bending strength sat below 45 megapascals, and shops that tried it mostly broke it. Hot pressing in the 1960s and alumina titanium carbide black ceramics in the 1970s made it viable. Then silicon nitride and whisker-reinforced grades pushed cutting speeds toward 4,000 surface feet per minute in cast iron and nickel superalloys, provided the setup is rigid and the operator forgives nothing. This is where the jet engine's bill came due. The superalloys that shrug off combustion heat also dump cutting heat straight into the tool, and it took whisker ceramics and purpose-built carbide grades to machine them at production rates. Cermets took the quiet lane. titanium carbide bonded in nickel traces to Peter Schwarzkopf's work in interwar Austria, spent decades too brittle to trust, gained nitrogen in the titanium carbonate formulations that Ford and others advanced in the 1960s, and matured into the fine finishing choice for steels, holding size and surface finish through long, unglamorous cuts. There's a parallel story running underneath all of this, told in grit instead of edges. In 1891, Edward Acheson, working just south of Pittsburgh, went chasing artificial diamonds with a carbon arc and a crucible of clay and coke, and pulled out hard crystals he named carborundum. Analysis showed silicon carbide, the first synthetic abrasive, patented in 1893, and that same year 60,000 grinding wheels shipped under a contract with George Westinghouse. Fused aluminum oxide followed around 1900 and became the wheel for steels. Vitrified bonds gave wheels that held their form, and precision grinding became how the world finished hardened parts. When GE pressed the first synthetic diamonds in 1954, diamond wheels made short work of grinding tungsten carbide. Steel was another matter. Hot iron drinks carbon, diamond included. The same lab answered. In 1957, GE chemist Robert Wentorf synthesized cubic boron nitride, trademarked Borazon in 1969, with the first American CBN cutting tools announced in 1973. It's the second hardest material known, and unlike diamond, it is chemically indifferent to iron, stable past 3,000 degrees Fahrenheit, where diamond burns around 1,600. Borazon went into grinding wheels first, chewing through hardened steel and high-speed steel, and sintered CBN inserts, then carried it to the lathe. That inertness created hard-turning, single-point cutting of hardened steel at 60 Rockwell C, work that once belonged exclusively to grinding wheels. A hardened shaft or bearing race that used to move across the shop for finish grinding could now come off the lathe at final size, no grinder required. Its sibling, polycrystalline diamond, sintered under the trade names Compax and Syndite, owns the other side of the map: high silicon aluminum, composites, anything abrasive and iron-free, where tool life against carbide can run to 100 times. Point it at steel, and the carbon dissolves into the chip. Every super-hard material has a lane, and the lanes don't overlap. Geometry has its own revolution running the same years, and it starts with a patent from 1863. Before it, a drill was a flat spade of forged steel, hammered to a point and hand-ground. Then Stephen Morse of Massachusetts patents the twist drill, 2 spiral flutes and a straight-cutting lip, patent number 38,119, and founds the Morse Twist Drill and Machine Company in New Bedford the following year. His drill form is still the world standard, and his self-holding taper still carries his name on every drill press quill. That taper grips under axial drilling load and was never meant for the side loads of milling, a limitation that would matter a century later. Few designs in any industry have held for 160 years. His has. The twist drill also picked up siblings, each built for a job it couldn't do. Taps split into families: spiral point guns that fire chips forward through the hole, spiral flute taps that haul them back out of blind ones, and forming taps that cut nothing at all, cold forging the thread into the wall for a stronger profile, and several times the tool life. Broaching came out of the 1850s keyway shops, and after the First World War, it took over rifling gun barrels, a gang broach pulling roughing, semi-finishing, and finishing teeth through the bore in a single stroke. Gun drilling was born in barrel making too, coolant pumped down a single flute carbide tool that holds a straight bore at depths past 300 diameters. And in 1977, drilling joined the insert age when Sandvik's indexable U-drill set 2 carbide inserts on a stubby bar and made holes around 10 times faster than a high-speed steel twist drill. End mills traveled further from their origins. The plain 2-flute and 4-flute high-speed steel cutters of the mid-century gave way to solid carbide bodies with 5, 6, and 7 flutes, and then designers attacked chatter at its source. Vary the helix angle along the flutes, vary the angular pitch between them, and the regenerative vibration that once dictated shallow, timid cuts loses its rhythm. American specialists like Niagara and Helical built their catalogs on those geometries. Tool paths evolved to match. Trochoidal and dynamic milling strategies, sold under names like Volumil and Mastercam's Dynamic Motion, keep radial engagement light and constant while varying the flute length in the part at axial depths up to 4 diameters, spreading heat and wear along the tool instead of concentrating it at a corner, with chip-splitting edge geometries added to break the long chips those cuts produce. High-feed cutters use a shallow lead angle to aim the cutting force up the spindle axis and trade depth for speed. Coolant now arrives through the tool itself, fired out of ports at the edge, because flooding from outside never reached the bottom of a deep pocket. None of it works if the tool moves in its holder. Morse's own taper is self-holding under axial load. That is why it survives in drill presses and tailstocks. Against the side loads of milling, it is helpless, so milling standardized on the steep tapers, CAT and BT. They served for decades. But at high spindle speeds, a solid taper and a spinning spindle bore grow apart. In the early 1990s, German industry and the machine tool labs at Aachen developed the HSK interface, short for the German term for hollow shank taper, a hollow shank seating on the taper and flange face at the same instant, shaped so centrifugal force tightens the connection instead of loosening it, with repeatability inside 2 microns. It became a DIN standard in 1993 and an ISO standard in 2001. Around it grew modular quick-change systems like Coromant Capto, shrink-fit holders heated to swallow the tool and cooled to grip it, and hydraulic chucks holding runout to a few microns because a coated carbide edge spinning at 30,000 revolutions per minute punishes every micron of error. And the edge is still moving. Substrates have gone to nano-grain carbides fine enough to hold a sharp edge on a tool thinner than a pencil lead. Tool bodies are being 3D printed with conformal coolant channels no drill could ever produce, and Kennametal stood up a dedicated additive manufacturing unit in 2019 to make them. Sandvik's Silent Tools line began as tuned, damped bars for long overhangs. The Plus versions now carry sensors inside the bar itself, streaming vibration and temperature over Bluetooth from deep inside a bore no operator can see. It is part of a wider push, Sandvik's Coro Plus platform among the flag carriers, toward machining that measures itself, chatter caught inside the bore before the operator hears it, surface finish flagged before the part is unclamped. After 100 years of machinists reading the edge by chip color and sound, the edge has started reporting back. If you made it this far, this channel is for you. Don't forget to like and subscribe. You might be interested in the video on screen now.